as we stayed off, I'd say it is a very great pleasure to be here, particularly as the opening technical speaker.
Yeah, Dr. Kuhn, your slides, I guess you can, sorry to interrupt, I mean, you can go to the slides maybe. Yeah, thanks.
Yes. Cool. Today, I would like to give you a general overview talk. In the tradition of leading off this colloquium, I will give an introductory talk. This is targeted toward undergraduates. My hope is to spark an interest in you in pursuing E&M as your field of choice. And I think a great introduction to E&M is to start with filters. This is my area of expertise personally. Today, we're going to be discussing the theory behind filters. And by the time you leave today, I hope that you will have an intuitive understanding of how they work. As Dr. Sarkar mentioned, my background is in filter design. I'm here today because I am the Women in Microwaves coordinator for the Microwave Theory and Techniques Society, and I'm also the coordinator for the MGA committee. In that role, I see a great many chapters, and it is an especial pleasure to be here at the request of the Kerala chapter. Chapters across the world do great work, but it is particularly an honor to be invited by Kerala. I've enjoyed seeing all your activities in the background, and we at MGA are very happy to support you. After this talk, if any student would like to connect with me, I invite you to find me on LinkedIn. I am more than happy to network with you. I see that as one of the great benefits of the Microwave Theory and Techniques Society. In fact, I myself have been a benefit of that generosity by meeting such persons as Dr. Cole, Dr. Nuno, and many, many others, including Dr. Chinmoy Saha. Okay. So let's begin. In the spirit of making this intuitive, we're going to assume no mathematical background. We're going to start with the very basics, physics. So in physics, energy is everything. We talk about how it got here, where it is going, how it transitions to new states. We tend to think of biological as separate from magnetic, but in the end, they're all the same thing. And so when we talk about E&M, electricity and microwaves and magnetics, we're focused on describing waves. As a very basic starting point, I'm going to say it's lucky that we know light is a wave. This is actually fairly new knowledge. And I think to have an intuitive understanding of it, you really should prove to yourself at least once that it is actually a wave. So as a historical tangent, you've probably seen this sort of diagram inside your high school science textbook where they lay out the different wavelengths. They give you a general size idea on the frequency. So in today's lecture, we're focused in the gigahertz. This is 10 to the 9th frequency range. If you go out into the commercial world today, there is definitely a continuing demand for filters in this range. You also work in the megahertz range and terahertz range. Honestly, we're getting there to where it's quite practical for industry. So starting off, how do we know light is a wave? How do we know that we can treat the subject matter as waves? So it actually happened that measurements preceded theory. This is often the case. In the early 1600s, experiments were proposed to measure the speed of light. By 1676, someone had actually managed to get a fairly decent estimate of the speed of light. They put it down to 22 minutes. They were actually better than that. The source of inaccuracy in their measurement was the diameter of the Earth, which they didn't have a means of determining at that point. And then in 1856, using the Leyden jar, folks were able to determine the value of the electrical permittivity constant and permeability constant, which comes out to the speed of light. But it wasn't actually until 1864 when Maxwell proposed his famous equations that we use in all aspects of E&M these days that we actually had a codifying of electromagnetic waves and equations that would predict that light, that these waves are in fact light and travel at the speed of light. We know a very special property of sinusoidal waves, and that's you can relate a wave's behavior in time to its behavior in space, factored by its velocity. Now, you may have seen in your introductory mathematics that when you have a relation with the first derivative, where the The velocity is related to the position. You either have a system that converges to a steady state or has runaway acceleration. But if you have the second derivative in time tied to the second derivative in space, you have a system which is rotational energy. These are things to describe springs and such. So if you were to take Maxwell's equations and you found that you could arrange it in this format, you would have effectively proved that you are dealing with sinusoidal waves. And that is exactly what folks did. I want to take you through it. I hope that you will see it many times again. These Maxwell's equations can be intimidating the first time you see it. I myself remember this quite well as a student, and I think that the more opportunities you have to ask questions on it and to be exposed to it, the better off you'll be and the more intuitive it will begin to feel towards you. So the first law, of course, is Gauss's law. Electric field diverges from a point charge inside of it. This is read del dot E. The next law is not named after anyone, but it's that the divergence of the magnetic field is zero. So this basically means you can't separate the magnetic field into a positive source and a negative source. Unlike electric field, magnetic fields are a full loop. You will never have excess flux entering any area. The third law, Faraday's law, says that a spatial difference in electric field will cause a time-varying change to your magnetic field. And the fourth law, Ampere's law, relates spatial differences in magnetic field with time-varying electric fields. So it's fine to not follow the math on this, but I wanted to leave you with a reference to it for how we rearrange Maxwell's equations to the point where you can see that they fit this periodic sinusoidal form where we relate position with time variance. So we start off with Faraday's law, where we have the cross of the electric field equal to the time-varying magnetic field. And since what you can do to one side of the equation, you can do to the other, we take the cross product of both sides. So if you follow along on the left here, there's a special property when you have the cross product of any vector field, and that is transformed by mathematical property into the negative del squared cross E plus del dot E. Happily, we already have a law, it's highlighted here in green for you, del dot E, which is how a magnetic field propagates from around a charge, is zero if you're in vacuum, because in vacuum you have no charge, therefore you have no electric field propagating around the charge, and so we get to cancel this term out. From there on, the left side of the equation is del squared cross E. So you see we've already got the first part of the equation we're solving for. This is the right-hand side, c squared of the partial derivative squared of u with respect to partial derivative of x, the second partial derivative, excuse me. So the left-hand side was pretty easy. We've already got it in the form we're looking for to prove that this is a sinusoidal system. Let's work on the right-hand side now. So we take the cross product of the partial derivative of the magnetic field with respect to time. And one of the mathematical properties is we can swap the position of partial derivative with del. And so we make a simple swap on line 2. Now you'll see we've come across another Maxwell's law, del cross B, how a magnetic field and electric field are related. So we substitute in the blue highlighted law. And again, we get a lovely effect that in a vacuum, we have no current flowing, and therefore that term crosses out. So now we're left with the partial derivative with respect to time of the partial derivative of electrical field with respect to time. So there we've done it. We have related the time-varying position of electric and magnetic fields with their position in space. So we know for certain that this follows the sinusoidal system, and we can also say that c squared, the speed of light, is 1 over the square root of mu naught E naught. It falls out of the math. Okay, so now that we've had the mathematical view of things, I want to take some time to go through with you what filters are like. I've spent most of my career in filter design, and the techniques that you use transfer very well across technologies. So whether you're doing things on aluminum, like this microstrip example here that I've copied off of the web, or you're implementing filters in semiconductors, which is what I did in my last role, you're going to be using the same basic theories and techniques. Okay? In our world, filters are used all over the place. There are probably several hundred in your cell phone at this point, because the more frequency bands we go up to, the more you need to filter out specific frequencies and block ones that would disturb the rest of the system. But we can start approaching the subject with a very simple prop, which is a tuning fork. Some of you may be musicians on the side. You've probably seen something similar to this. When you whack one end of it, which I will do here, it creates a humming noise. And this is tuned to a specific frequency. The frequency is set by its length, and it rings in the air. So this is very similar to what is going on in an E and M filter. Okay? Our whole goal when we design filters is to have some frequencies get through them and to block entirely other frequencies that we don't want. So we've convinced ourselves that these things are waves. Now the question is, how does energy pass in a filter? What is actually physically going on there? Okay. It's very similar, going back to the tuning, to the idea of sound waves and guitar springs. This picture that I have shamelessly copied from Wikipedia shows a microstrip style filter. It's called a half-wave resonator, which means that each one of these lines is a half wavelength in electrical length. On the bottom side of this filter, there would be a solid plane of metal. This functions as the ground plane. It's the reference plane for the filter. And at some frequencies, when you look at one of these resonators, a standing wave is going to be able to form. So a standing wave could be the fundamental frequency, which I'm showing here on the right-hand side, where we have half a wavelength with its nodes at either end. It could be twice that, 3 times that, 4 times that. All of these modes are energetically able to build in this resonator. So that this resonator functions very well to carry energy at this specific frequency. And as we move away from something that isn't one of these frequencies, consider like 1.2 F naught, it wouldn't be able to form a standing node anymore. And so that energy does not build on side of the resonator. Okay? Those of you who are musicians know what it is like to hold a tuning fork in one hand and put another tuning fork next to it. The one that's ringing, the sound waves mechanically transmit through the air, they hit the other tuning fork, and you begin to hear that resonance as well. Perhaps you have held a drinking glass in your hand when a large truck rolled down the street and you have felt the vibrations in it. It's a very similar idea. The electric and magnetic fields spread around the metal conductor. The bulk of the energy is inside the dielectric. The dielectric is the material that is between the two metals. And then we lose some fraction of the energy into metal, but most of it is able to form a standing wave resonance. And once it's in a standing wave configuration, it's not being attenuated, and so it is able to ring, and that ringing energy is transmitted to the adjacent resonator, and that is how it propagates through. So let's look at some cross sections of what the electric field and what the magnetic field are doing. If we were to cut this filter, if we were to cut this filter down the dashed line you see on the screen and hold it up on the side and look at the cross-sectional view of it, you would see something that looks like the graph on the upper left. You have a backside metal plane, that's the ground reference, and then you have the top narrow strip, which is your resonator, and in between you have some sort of dielectric material. Around that, you have electric fields, which are going same as you learned in your introductory physics class. They're going from the plus to the minus. So you're building electric field in that dielectric. And the magnetic field is circling around the resonator. If you remember the right-hand rule, the current is flowing through the resonator, wrap your hand around it, and then you get the magnetic lines. If we were to try and color code this picture a bit to make it a little easier to understand what's going on, we have our E&M wave, where we have the electric field moving vertically in this picture. We have the magnetic field in and out of the page in this picture. So the red lines would be the field. You see some of them wrap through the air, then go down into the dielectric before reaching the ground plane. Some of them are entirely contained in the dielectric material when you're directly underneath the conductor. And then the blue oval indicates where the magnetic line is. Okay. So at our resonance frequency, the F0, which is where the standing waves are able to build, we have a repeatedly changing electrical field, which generates a repeatedly changing magnetic field. Because these things are waves, they propagate all around in space until they're fully attenuated. And because we're in air and low loss dielectric, it takes a while to attenuate them. And then they reach the adjacent resonator. When they reach that adjacent resonator, they set up another standing wave. And so at each one of these resonators, if we were somehow able to look at it, we would see this standing wave at our fundamental frequency, our second harmonic frequency, our third harmonic frequency, and so on. And you can keep doing this. You can chain together as many resonators as you like until you run out of energy, either by attenuating it through the metal loss, through the dielectric loss, or so on. So if we look at a photograph of a microstrip filter, such as this one from Wikipedia, we can actually intuitively say an awful lot about it. At first glance, I think it's kind of weird to think of energy propagating through these things because there's no DC connection, but because they're waves and you get this standing node, they're able to do it. So the length of the resonator determines the length of your standing wave. So if we were to measure one of these with a microscope, or if they're large enough, even a very good ruler, you would be able to know with pen and paper calculation, what is my center frequency? If we have a longer resonator, then we have set up a longer half wave because this thing is resonating. And then we have a different fundamental frequency. Okay. The spacings of the resonators, by which I mean the spacing between the top resonator, the second resonator, the third resonator, and so on, that tells us how many tag-along frequencies are able to go along. Because we've talked about the fundamental frequency setting up a standing wave, but it's not just the fundamental frequency that's able to get some energy propagating. You have other modes, some of them are effervescent and die right out. But when you're very near that fundamental frequency, you also have a fair amount of energy that's contained and can build up a resonance and propagate through your filter. So when you want a high bandwidth filter, you want a filter that can pass a large range of frequencies, you'll see them designed where they have these resonators spaced closer together. And when you want a very narrow one, you might have a very wide gap between resonators. So without knowing anything about Maxwell's equations, really, without doing any EM simulation, you can look at these things and still know a lot about what's going on. Now, the ratio of the spacings. In this example, we have 5 resonators. So we have 4 different spacings between them to consider. The ratios between these spacings tell us the shape of the filter. How quickly does it attenuate the frequencies we don't want? How flat is the pass band? You may have heard your professors talk to you about these Butterworth or Chebyshev style filters. And this is where you see them practically implemented in the spacings here. The number of resonators, that's the order of the filter. You may have had a design example where you were asked to design a 3-stage Chebyshev filter, for example. Well, the order is the number of stages, and that's the number of resonator poles in here. So the example on the screen is 5-pole. The number of resonators determines how quickly you're able to attenuate the frequencies you don't want. And we're going to go through this in a practical lab because I think it's very valuable to match theoretical knowledge with practical knowledge. I just wanted to say one last word about coupling coefficients because I think the first time filters are introduced in textbooks, they're often done with polynomial coefficients. So it's important to know that that's actually a little different than the coupling coefficient. So the polynomial coefficients are mathematically derived. They are what you would see in a book of filter tables that you probably have an appendix in your physics book, and if not, there's certainly a lot of literature on them. And mathematically, you are able to optimize the transfer function to get certain characteristics of a filter. There may be cases where you want an extremely flat passband, in which case a Bessel style filter is what you would choose. Or if you need a very sharp roll off, you would use an elliptic filter. And you could look up coefficients for this, which would look like the Butterworth polynomial coefficients I'm showing you on the screen. However, as a practicing engineer, you will never do this. What you will do is worry a lot about coupling coefficients. And coupling coefficients tell you how much electric and magnetic energy is going between your resonators. And they are loosely tied to the mathematical polynomial coefficients. They are related, but they are a little different too. Okay, so let's get to the practical part, the meat of this really. Today we're going to do some experiments using Sonnet Lite. Now I'm using Sonnet here because you can quickly download it off the web and install it. It's not necessarily my favorite EM software. I do like it quite a lot, but I also really like Cadence AWR software, which has the Axiom solver. And for your preparation for industry, it's probably also a good idea for you to look at tools like CST or ADS. Feel free to ask me in the questions section any details about this. If you'd like to follow along with the lab session, you should go to this link, sonnetsoftware.com/products/lite, and you'll be able to pull down the tutorial and go through this yourself. So as a component with classwork, simulation is a very quick way to build your intuition and to test that you understand the material. I highly recommend you to get a copy of some sort of E&M software. Many of the vendors are delighted to work with students and provide free licenses to you so you can get early experience with them. It's a good idea if you do get experience with EM software to list it on your resume. It is something an employer looks for. And if you're doing a design project inside one of your courses, then of course that's also something that you would want to list on your student resume. As a hiring manager, I can tell you that's certainly something that we look at. Okay, let's move to the lab section. Okay. If you've downloaded the software, you will see a toolbar that looks something like this. Go to the project menu and say browse for examples. You're going to get a tutorial menu, and today we're going to be using a quarter wave filter, which looks like this. It's called Fitwall. You can open it directly. I've already opened it to save us some time. Okay. What we see here is very similar to the half-wave resonator that we talked about in the lecture portion, but this is called an interdigital filter. It's a quarter wavelength resonator. Each end of this resonator is tied to ground. The ground is this box that surrounds my circuit, so anything that touches that is grounded. And then below this, we have an actual ground plane. So let me go ahead and show it to you in 3D. And a lot of the EM simulators have very lovely 3D graphics viewing it. It really spices up presentations. So I recommend you to get familiar with this. Sometimes you may just want it for the 3D CAD ability. Okay. So we have a filter. It looks pretty similar to what we talked about, except in this case, it supports a quarter wave instead of a half wave. And now we see how we have 5 resonators, same as our original example. So this is a 5th order filter. Okay. You analyze the project by going to the project menu and selecting Analyze. It will ask you to save it. I've already run it to show you guys here. And you get a response that looks something like this here in pink. Okay. So you can see it passes frequencies very well from about, I'll add a marker here. This is the edge of the band, 4.93 to 5.27. That's what we would call the passband in filter design. So this is where our standing waves are being formed. They're around our center frequency. I've marked it here for you to see. And then because, as we discussed, energy propagates around the fundamental frequency, not only exclusively at the fundamental frequency, we get this nice bandwidth. Now, when we go outside to the right and left, these are called the filter skirts. Okay? This is considered the roll-off region where we have attenuation. So if you are designing a filter to receive cell phone frequencies, for example, 2.4 to 2.5 is the Wi-Fi band, you would put your passband at 2.4 to 2.5, and you would try very, very hard to attenuate out the ISM bands and the second harmonic of that, the GPS bands, anything that might interfere with your module. And so the attenuation of the filter is important, and the steepness of that attenuation is very important. Okay. Things that you might do to test your understanding of this is ask, okay, what happens if I make these resonators longer? Or what happens if I have fewer of them? Okay. I'll show you an example here of just how easy it is to do this. I deleted the middle resonator. Now I have a 4-pore filter, and when I run it, I expect to see a different result. So think about in your head for a moment what you would expect 4 poles to look like. 5 poles was steep and it had a fair amount of loss. 4 poles is less steep. Okay, we've recovered some of our loss because we have less metal that's consuming the energy. So it makes sense that the passband is higher and that these, which we see here when we compare blue to pink, and then the skirts are much shallower. Okay. Now you might ask, what happens if we do the 4 poles flipped, which is really the proper way? You'll see that I broke the symmetry when I did this, so I can flip it back. This is the proper way to design an interdigital filter. And if we do that, we'll see recover the shape somewhat. Okay. Now you might ask, well, what does a 3-pole look like? So how would we do that? It's pretty easy, and you should play with this to get used to the software and get comfortable with the idea of being able to test these concepts of how many resonators with what coupling coefficients and what that results in. So if we run the three resonator version of it, let me show you what that looks like as well. Okay. So the 3-pole version now has even better loss than our passband range, okay, because we have fewer resonators, so less consumption of energy, but our filter skirts are even slushier. So as a filter goes, this probably has limited practical value, but there might be some application where it's useful. I'm going to pause for a moment here to let you enter some questions in the chat window if anyone has some. Savada, perhaps you could read them out?
So, no, so one person has asked, Rahul Kumar Thakur, he has asked, I want to ask that if we will design stepped impedance Butterworth low pass filter of fifth order, then can we find out directivity, gain, bandwidth of the filter? And if yes, then how? I tried to find it in the poster book, but I didn't get it.
So gain of the filter is a great question. And can you tell the gain of the filter just by looking? That's interesting. You can make some general assumptions about it. So an active filter, which is one implemented in a silicon, gallium arsenide, gallium nitride, so on sort of process, will have gain. Passive filters, the metric tends to be called insertion loss, but really that's the same thing as negative gain. And you can make an educated guess about this based on the number of poles, because you have more energy consumed by every time you have a resonator pole, and also by the dielectric material that the energy is transmitting through. So if we're in vacuum, we have no loss. But if we're in material like an FR4 board, which is the green board that you've seen when you take your PC apart and look at it, that is actually pretty high loss material. And so it has worse insertion loss. A higher negative gain would be another way to say that. Any other
Yeah,
questions?
yeah. So I guess thanks, King, for this wonderful talk. And I can see some question like Sivara actually has asked one point, like what is the difference of learning EM theory in real world industry scenario, or how different it is from the what we study maybe as a student in the theory, and what you have experienced probably in practice as your experience in the industry. So please comment on that a bit.
Sure. Thank you for asking. So the difference between the textbook filter experience and the industry filter experience, I found to be fairly extreme. In the textbook, we consider a lot of transfer functions. This would be S space, and you would be doing Laplace transforms and so on. You would be looking at the denominator of that transfer function to understand where the poles and potentially zeros lie in complex space. So it's a mathematical approach to it. But when you hit industry, you find there are all kinds of things that go terribly wrong very quickly. One of which is you can't actually implement these polynomial coefficients in the textbooks. The textbooks present everything based on inductors and capacitors generally. How do you transform these coefficients into particular L values or particular C values? But inductance and capacitance are really an emergent property. There's no such thing as a pure capacitor. At some frequency, each piece of metal will behave like a capacitor, and at some frequency, it will also behave like an inductor, and this changes as you move throughout frequency. So learning to deal with that in the real world, where nothing is actually frequency stable and nothing is actually a nice smooth dimension, really changes the ball game. You may want to design a great filter, but you might have the budget for very cheap materials. So
Right.
you might be able to implement something that's fantastic on Illumina or Rogers 4350 or such, but your budget is for the FR4. Or you may have the best filter design ever for having a very steep cutoff that would prevent your amplifier from overloading, but you're not able to implement it because the dimensional control in the manufacturing world is far from perfect. Some of these filter designs could be wonderful if they had tenth of a micron precision in manufacturing. But when you get out and order your FR4 board, you'll see they're only going to guarantee some dimensions to a mil or 2 mils. That's 25 to 50 microns. So you can't actually implement the filters you want because the precision manufacturing isn't there. And even if you did get a few of the filters to turn out, the manufacturing variation would completely swamp it. So
Right.
one last comment on this. Another difference between the study of filters and the industry usage of them is the amount of time spent with EM simulation. I saw a little of this when I was in school. I think our professors have done a great job of making students more exposed and aware of it. In industry, it's all driven by EM simulation. You will never sit down with a book of filter tables or a pen and paper calculation when designing a filter. You will jump pretty quickly into optimizing things through EM. And the simulation tools are phenomenally fast these days. It's the skill set is knowing how to efficiently use the software to get to a result quickly. In industry, there's a very heavy emphasis on getting to the final design quickly so that the product lifecycle can move forward.
Right. Yeah, so thanks very much for this. I guess you covered many points that would be very helpful for the students like Sivara. I think there good amount of the participants that we have are students and young engineers. So I think this will be great for them. So also on the same line, there is another question that could you kindly share your journey and what inspired you to opt this domain of electromagnetics? And I mean, this is asked by, I think, yeah. So for all the young girls out there, any message or anything that you want to share here specifically?
Uh, I don't know if I'm supposed to admit this or not, but I kind of fell into RF by accident. All of my friends were doing electrical engineering when I went to school at Caltech, and so I signed that up for my major as well. I was pretty torn between materials and electrical, um, but in the end, I was won over by electrical, and I started off at Intel doing low frequency R&D type work on what materials we should be using in future designs. And then a friend of mine asked me to interview at his company. That hiring manager was looking for someone to design front-end modules, like could go into cell phones and such. And so that was my first exposure to RF. I actually saw very little of it in school. But I would say to anyone considering the RF field, it is interesting technically. You get to do work that is somewhat on the border of engineering and science. So I highly recommend it to all the young persons out there.
Right. Yeah. So yeah. So I guess we have actually with us. I can see in the attendee or participant list, Dr. Sudhakar Rao, all the way from California. So if you are listening to us, Dr. Rao, you can unmute yourself and maybe like interact a bit. Dr. Saha, can you see Dr. Rao over there?
Yeah.
Yeah. Hi.
Good
Yes.
evening, Dr. Rao. Please turn on your video and offer your comments. This is a wonderful initiative on women on microwave and antennas. And he has been really phenomenal in supporting us. Sometimes I get reply from her even before I finish my email. Yeah, Dr. Rao. Yeah.
Yeah, you caught me right on time. I was about to go to bed, but okay. I got your text and I thought maybe I should wake up and talk a bit. But great initiative, I think, Chinmay. I think, I think women in engineering is very important to IEEE. And out of all chapters, I think Kerala is doing the best promoting the women in engineering. I think your students, I think I've attended Trivandrum a couple of times in ISA workshops. So I think the quality of women engineers are amazing, actually. I'm really impressed with some of the students. I think Subhada and before that Kirti Priya, and now I think you have another young batch of bachelor students coming up. Grishma and Lakshmi. So I think great talent there in Kerala, and I think Kerala chapter is doing very good actually. Not only women in engineering, but also MTT and organizing, especially in this pandemic, several events. I think several of them is very novel. I think like L4 and other events as well. So very, very useful to students. And I think your Kerala chapter with your leadership and Anu and a few others, I think Dagdeep also now I think is a new star now. I think is emerging star now with YP and joining IIC also I think helps a lot. I think very great initiative, and I think we have wonderful speakers. I think I just heard something on the filters, very interesting. So I come from the industry, so I know what all the problems with filters. You design filter, of course, when you make it, it doesn't work. So a lot of things I think you have to learn, especially when you have high Q filters. I think everything is you're looking for low insertion loss, pass band, especially when you design for space. You have to take into thermal effects and then rejection into other bands. Sometimes you have to reject 40, 50 dB, which is not easy. Sometimes in waveguides we reject up to 80 dB. So theoretically, it's almost impossible, but I think if you're in the industry, I think if you have the right attitude, I think you can design it quickly. So thanks. It's a great talk, and hopefully students will benefit from all these talks. I think from the women leaders in microwaves. I think that's a good thing that we have a new president coming up, president-elect woman. I think probably second woman, and I think a lot of people in line. Looks like I think we need women leaders now. I think hopefully APS also will follow it a bit. I think it's coming in all IEEE nowadays. I think not only in IEEE, but actually in the industries. I think we're supposed to promote all the women engineers into management and technical positions. So if you're a woman, I think if you're in antenna and microwave area, I think this is very good because a lot of shortage of talented people. So learn from your guides and teachers, and not only learn but also practice, and the attitude is very important. So don't work hard but work smart. So thanks for all attendees, and Chinmay, thanks for organizing this great event.
Yeah.
Over to you.
Thank you.
Thank you, Dr. Rao, for the wonderful comments, and thanks to Kim for this wonderful lecture. And I personally,
can I have a comment? Can I have a
sure.
Yeah. My comment is to Kim. Kim, nowadays there are some kind of new research directions on so-called metamaterial inspired filters, etc., etc. These are all, evolution of the same old stuff, but in a different way. So, considering this and considering the well-established theoretical techniques in designing filters, so what do you think? In next a decade or so, the filter design research is going, especially from industry perspective?
I'd say the great thing for potential filter designers and also for educators is the fundamental theory doesn't change. We get better materials, we have things that have negative coupling coefficients, we can do fun things with cross coupling and so on, but the fundamental theory doesn't change. So the educators who give their students an intuitive feel for the basics have prepared them very well for the future. And I would say from the industry perspective, that when I hire someone, I'm not particularly worried about their ability to learn a new technology. If they've been successful in one, those same skill sets will carry them over into my particular technology. So it's a versatile field in that respect.
Right.
Yeah. So one more question. Is there any opportunity for students, especially from this part of the globe, to have some internship, some short duration work, etc., in industries in general and in particular to your organization?
So internships are a great way to get in the door. Usually companies start looking for the interns about 6 to 9 months before the summer break. So if that is something that interests a student, they should know that they need to begin looking early in the winter. area. Now, in the US, it's unusual for a company to want to pay relocation for any intern, no matter where they're from. But if you're an international student and you would like to stay nearby your university over the summer, look for the companies nearby. One thing I would say to students is that your choice of specialty can have a big impact on where you can live. For example, in the US, if you're specializing in power electronics, you're probably going to be near the center of the country. Whereas if you're a filter designer, odds are pretty good you're going to be on the coast just because that's where the work lies. And if students aren't sure about what they're considering, they should network with people at their university from the career centers and also professional development groups like this one, MTT-S and APS. It's really wonderful to get insight from people working at those companies if that's the one that they want to go intern in.
Yeah, yeah. Thank you very much. So one last comment from my side is we are very good in filter and filtering. That's why we have very good people, great people around us, you know, like you and like other people from the AP and MTT society. Yeah, thank you. Over to you, Dr. Sarkar.
Yeah, I mean, well, I guess we are almost on time, and I'd like to thank Kim for this wonderful lecture and for all the participants. I could not take all of their questions, but I guess you can maybe contact with me or contact her through LinkedIn, as we mentioned, to get your queries. And personally, I really liked that one slide that had the guitar in it, and you actually drew parallel with the acoustic and the electromagnetic part side of the things. So I really like that one. So yeah, over to you, Dr. Saha, for like you can formally conclude, I guess, this particular session.
Yeah, I think Sivada might take again a virtual photo shot because that's what we planned, that will capture each of the session. Sivada, you may please announce, and then after that you may conclude.
Right.
I request all the participants to turn on their videos so that we can have a photo shoot. Thank you. Thank you all.
Sivada, you may please formally announce about the next session and then conclude.
Sure, sir. The next session will be on at 6 p.m. IST today. So it will be by Dr. Slatika Maringovic, ma'am. She is from University of Minsk. It will be on some artificial neural network applications and electromagnetics. So hoping to meet you all there. Thank you everyone for making this event a grand success. Thank you.
Thank you very much.
Thank you.
I'm really overwhelmed to see the President MTT-S still awake and be with us. And Dr. Siddiqui, Dr. Rao from Northrop Grumman. Thank you so much for your overwhelming support. And Sherry also. Thank you so much. Yeah.
Thank you, Mike. Thank you, everybody.
Thanks.
Thank you.
Thanks, everyone.
Bye.
Bye. And see you.
Yeah.
Yeah.
Have a good day. Bye.
So much.
Yeah. Bye-bye.
Bye.
Bye.